Hi, everyone. Welcome to this talk. I changed the title a little bit. So this will be still an Electron talk, but not just Hello World. And I'll cover some practical tips of Electron development here. So hello, my name is Vanessa. I work for GitHub. I'm an engineer on the Electron team. So I want to start off by talking a little bit about what life was like before Electron. Before Electron was born, if you were a sole developer and you decided to build a desktop application, you had quite a few choices in terms of technologies. But first, you have to think about which platform you want to target first. So let's say you go with Mac, and you decide to use Cocoa. And you built this amazing app, and it's doing really well at the App Store. People love it. And then you start getting like Windows user pinging you, be like, hey, what about us? And you're like, OK, well, maybe I should consider making my app available for a Windows user as well. And guess what? There wasn't a whole lot of easy solution that would allow you to reuse the code you already wrote for your Mac app and build this window app that you wanted to make. You basically have to build two distinct applications, one for Windows and one for Mac. Cross-platform was hard. And there were some cross-platform solutions like Qt or Adobe Air. They didn't really, well, at least for me anyway, they didn't really pick up. And some of them were, the learning curve was just a tiny bit too steep. Thankfully, thanks to web standards and the cooperation of browser vendors, we do have something that is cross-platform, and that is the web. Web apps built with HTML, CSS, and JavaScript are interpreted and recognized in almost the exact same way on every single platform. So Electron project is unique in a way that it decided to bring the cross-platform compatibility from web to desktop. How does it do that? There are two core pieces of Electron. One is the Chromium, which is the underlying engine of Chrome browser and Chrome OS. And that is the piece that allows you to use web technology to render stuff on the desktop application. And that combined with Node.js, which gives you access to the file system. So these two pieces, plus some love, that became Electron. And today, Electron is used by many big companies. And you probably are using some Electron apps on a day-to-day basis, like Slack, Skype, Visual Studio Code, Atom, et cetera, et cetera. So with so many success stories, that must mean Electron is the perfect solution to building a desktop application, right? Well, I mean, Electron did lower the barrier of entry to desktop applications significantly. But from web to desktop, it's still not a completely challenge-free journey. There are a lot of gotchas. So this talk, I'm not going to talk about how to build an Electron app from scratch, because there are already many, many, many talks and many online resources on that topic. Instead, in this talk, I want to have an honest discussion about some of the obstacles that you might face when you decide to build an app in Electron, why these obstacles exist, and what you can do to get around them. OK, so before I can get to that, first we have to talk about how the general architecture of an Electron application. The entry point of every single Electron application is the main process. There can only be one, never more. It's your typical node process with Electron APIs, which allow you to do operating system tasks. The main process can display a GUI window by creating a renderer process. A renderer process is almost exactly like a web page, with the exception that it has node enabled. And it's not sandboxed, meaning that within the renderer process, you can still have access to the file system unless you explicitly tell it not to, which we'll get to in a bit. What else? Right, so calling any operating system related API is not allowed from the renderer process, because it's dangerous and it's very prone to leaking resources. So what do I mean by operating system related tasks? So for example, displaying notification, resizing the window, that sort of thing. So if you want to do that from the renderer process will have to talk to the main process and be like, okay, can you display this notification, please? And then the main process would do so. The two processes talk to each other through this thing called IPC, which stands for inter-process communication. And they use this to send messages to each other. While there can only be one main process, you can have multiple renderer processes. The main process would manage all its renderer processes. However, each renderer process only cares about the web page it runs inside of it. So to quote my colleague's analogy, you can kind of think of the main process as the puppeteer, its renderer processes as his puppets, and IPC is kind of like the strings that he uses to control his puppets. Okay, so what does that look like in code? So first you define an HTML page to show as your main window. As you can see here, it's nothing fancy, just simple hello world. And then you define an entry point for your main process, which we'll call main.js here. And you would use this Electron API called browser window to create an instance of the application window. That would be your main window. And actually, when you create a browser window, it will also create the renderer process that would manage it. And then you tell it to load the HTML page we had just written about it. And after that's done, you should just be able to do Electron main.js and hello world. Simple, right? Yes, so this talk is not going to be hello world, like I said, like I promised. So now that we got the architecture of an Electron app down, we can talk about the rest of the talk. So first thing, don't block UI thread, and also don't block the main thread. If you come from a more like a web development background, which I assume a lot of you are, you probably are familiar with the concept of and the importance of not blocking the UI thread. Because JavaScript is single-threaded, meaning that if you run any intensive task, so I don't know, like if you convert a video or something, it will block the entire UI thread, meaning that users will not be able to scroll or click or have any kind of interactions with the UI. So not ideal. And since that Electron has this concept of a main process and a renderer process, it's very easy to think of the main process as the back end and the renderer process as the front end. And as a result, a lot of a common first attempt to unblock the UI is to move all the heavy lifting stuff to the main process. Makes sense, right? Except it's not a good solution because the main process is also single-threaded. If you think about the analogy we just used about the puppeteer and his puppets, if the puppeteer is busy eating, he's not going to be free to do his puppet work. So basically, if you block the main process with a CPU-intensive task, the renderer processes are also going to be affected. So what do you do? Like, where do you put the CPU-intensive tasks? You can multi-thread it. And generally, in Electron, there are 3 ways of doing so. One way wins, and obviously, you're going to put the best way the last, so bear with me. First way is web worker. Because Electron is built on top of Chromium, pretty much everything that can be done in a browser can be done in Electron. Same as web worker, because it's a web standard. So the advantage of doing so is, because it's a web standard, there are many, many resources online of how to do so, and it's quite simple. It's just one line. I don't want to get into too much details on how to implement it, because A, it's exactly the same way as you would implement it on the web, and B, it comes with a really big caveat, is that within the context of a web worker, you will not have access to any of the Electron API nor native modules. I'll explain what native module is in a bit, but at this point, what you have to understand is that within web worker, you won't have any of the power or tools that Electron gives you. So that's not an ideal solution. The second way is you can consider forking another node process. If you have been using Node for a bit, you might have heard of the cluster module or the child process module. What they allow you to do essentially is to create children processes that have a communication channel with the parent process. And a parent process can be like, OK, kids, go do all these intensive work and report back when you're done. So that could work. But then again, within these child processes, they also don't have access to the Electron API. So that won't really be that powerful either. The third way is you can actually have hidden browser windows. So remember we talked about the difference between the main process and the renderer processes, and we talk about how each renderer process corresponds to a browser window. Turned out you can actually use the renderer process more than just rendering the UI. You can use it as a pseudo worker process as well. What you have to do is when you create a new browser window, you pass in the show flag and set it to false. So you're essentially hiding the browser window, but the render process is still running in the background. So and within that render process, it has all the Electron APIs. It can communicate with the main process, and it can use all the native modules that you want. So that's the winner of the three. If you ever have to do anything intensive, use a hidden browser window to help you with that. Second thing I want to talk about is cross-platform compatibility, because it is one of the biggest, if not the biggest, selling point of Electron is that it makes cross-platform app really easy, right? Well, if you go on the Electron website, the apps page, which features a lot of applications built with Electron, you might be surprised to find out that a lot of these apps are either Mac only or Windows only. Well, I mean, if developing for cross-platform is that easy, why isn't every single application available for every single platform and every single architecture? So this might come as a surprise to people just getting into Electron development. The cross-platform build does not happen automatically. And it's not that cheap to set up either. But I want to take a step back and say that this is kind of beyond Electron. I don't think it's Electron's fault, per se. In fact, I think Electron handles the coding part of cross-platformness pretty well. There are specific APIs that are available in one platform, but not the others. But they're all very clearly documented and quite easy to work around with. It's actually the building, the packaging, and the code signing part of making a cross-platform app that makes it complicated. Now, what do I mean by that? First, we have to talk about native modules. So I kind of touched on native modules a few slides back. At a very high level, native module, or sometimes called Node.js add-on, is a library written in C or C++ with a Node binding, so you can consume it from Node. And how you use them is actually the exact same way as you would use any other Node module. You just do a require statement. And native modules became a thing because, well, it's written in lower level languages, so they are more performant. And they're also good for doing any kind of like OS level operations. And I know, most of the NPM modules out there are not native. Only about 400 out of 650,000 are native modules. And how you know is if you do npm install something, like node sass is one of the, I guess, like a more known one. If you see that in the log it says like download binary or like compiling something, is generally a pretty good indicator it's a node module. A native node module. Right, why should you care? So since the consumption of a native module is pretty much exactly the same way as you would consume any other node module, there's a very high chance that even if you have native modules in your dependency in your project, you would not know that they are native modules. And I mean, really, why should you? If you're just writing JavaScript for the web, it makes no difference to you whether that dependency is a native one or not. However, if you are writing JavaScript for the web, it makes no difference to you whether that dependency is a native one or not. However, if you are writing JavaScript for the web, it makes no difference to you whether that dependency is a native one or not. However, if you are writing JavaScript for the web, it makes no difference to you whether that dependency is a native one or not. However, That matters when you're writing an Electron application. The reason is that because these modules are lower level and they often have to do with operating system-specific APIs, they need to be compiled for specific architecture and specific operating systems. So to put it simply, a native module compiled on my Mac, if I were to not do anything fancy with it, is not going to work on a Windows machine, even though a regular Node module would. So now you can see why this would be a problem when you're building an Electron application, and especially if you want to make it cross-platform compatible. So what's the solution? Is it just to avoid using native modules? You can try. I mean, and it's not that hard because, I mean, like, there are only 400 native modules, right? And if you can somehow avoid using them, they do decrease the complexity of building for cross-platform a lot. But if your app needs to do anything, say, for example, if you're building an Electron app and it somehow needs to access the user's keychain on their system, for example, as far as I know, there's no other way to do it aside from using this native module called Node Keytar. So it's hard to avoid. So the recommended solution here would be actually to use different CI for different platform that you want to build for. So one for Linux and OS X, and one for Windows. If you're making an open source non-commercial project, you can get these CIs for free. But if your apps is closed source, that would essentially mean that you have to spend twice the money on CI if you want to build for two platforms. And this is only the build part. There's the code signing part. Code signing, the one-liner is that it's a security technology that you use to certify the app the user downloaded and installed is indeed the one that you built on your machine. And you can kind of think of it as like the verified icon on Twitter. Yeah. So if you don't sign your app, when a user tries to open it, this is the kind of warning they'll get if they're on a Mac. And on Windows, it's even weirder, I think. It's something like, oh, you're protected now. It's weird. So if you're building an Electron app that you intend to package and distribute, it should be code signed, because I mean, this looks pretty sketchy. And also, if you intend to put your app on Windows App Store or Mac App Store, they don't allow unsigned apps, so you have to do it. The way you do it is you have to purchase a developer certificate, one from Apple and one from Windows. And then there's like some code signing magic you have to do. And unfortunately, you can only code sign a Mac app from a Mac and a Windows app from a Windows machine. Yeah, I know. So yeah, cross-platform is still hard-ish, but it's not really because of Electron, but because of all the restrictions that these operation systems put on it. The next thing I want to talk about is security. As web developers, we're really, really blessed in a sense that we don't really have to worry a lot about the scary security stuff. And the risks associated with the code we write are relatively small. And that's because websites don't really have a lot of power when they're just in a browser. It cannot really get outside of the browser tab that it's contained in. And we generally trust browsers a lot. We trust that there's smart people working on these browsers that we're using, and they're built by a large team of engineers, and they should be able to respond relatively quickly to any newly discovered security threats. But working with Electron is very, very important that you remember Electron is not a browser. JavaScript running within the Electron context can have access to the file system, the user shell, and many more. It gives you a lot of power, but you know what comes after the sentence, right? With great power, exactly. So yeah, it gives you a lot of power, but the inherent security risk is significantly higher as well with Electron apps. If you need to load anything remote in an Electron app, ask yourself first, do you really need it? Do you really, really, really need it? In fact, most popular Electron apps, so Atom, Visual Studio Code, GitHub Desktop, They display primarily local content. And if your application executes code from an online source, it is ultimately your responsibility as an app developer to make sure that this code is not malicious. If you really have to load remote content, there are several things you should make sure that you're doing. First one, only load secure content via HTTPS. So don't use HTTP or FTP. You should be securing your server by now, I think. Second thing, disable node integration in any renderer that would render remote content. So cross-site scripting attacks or XSS attacks are quite common. They refer to this kind of attack that injects malicious scripts into an otherwise trusted or benign website. Their power is, again, they're not too bad. Usually you just worry about if they will mess with your website, but that's it. However, in Electron, again, because it's not a browser, it is a lot more dangerous if that JavaScript executing on a remote server can jump out of the renderer process and mess with the user's computer and read their files. So disabling node integration limits the power you give to remote content and make it significantly more difficult for an attacker to harm your users by gaining access to execute JavaScript on your website. So how do you do that? When you create a new browser window, you set node integration to false. But that does significantly limit what you can do in that renderer process, since now you will no longer have access to Node from there. So what you can do in addition to disabling node integration is specifying a preload script. You can still expose explicitly defined APIs to your website that do consume Node modules or features. So the preload script will continue to have access to require and other Node.js features. So in this example specifically, the loaded website will then have access to this window.readconfig function that we specifically define, but no other Node.js feature. Third thing, handle session permission requests. You probably have seen those warning dialog that pops up when a website is trying to send you a notification or access your location or your webcam and stuff. By default, Electron automatically approves all permission requests. And that's bad if you're loading remote stuff. So if you're loading remote content, you should be more security conscious anyway. And so in this situation, you would want to define a permission request handler. So you just use this API called setPermissionRequestHandler, and in there you add logic to either approve or deny requests, permission requests. Fourth thing, eval, override it. Eval is a core JavaScript method that allows execution of JavaScript from a string. And it's good for, it's written specifically for executing JavaScript that is not known ahead of time. And there are a lot of legitimate use cases of why you would want the eval. But if you're loading remote content, it's very hard to make it bulletproof, but easier to just disable it. So if you're doing that, if you're doing remote content and you don't have a very, very strong case of why you need eval, you should probably disable it. And you would do so by defining a new eval function that overrides the JavaScript default with an empty or no-op function. On the Electron website, there is a more comprehensive list of all the security recommendations. I only have time to go through a few of these items, but I highly, highly, highly recommend any Electron developers to go through this list, make sure that their Electron app is doing all of these things. So this is a quick tip and an easy win, in my opinion. This is the quickest and easiest way to speed up the startup time of your Electron app is to limit the number of require calls. When you require a module, what actually happens is Node has to first locate the module, be it from your Node module folder or elsewhere, and then it reads its content synchronously, and then it compiles it, and then it executes it. And it does that for every single require call. So require calls are actually quite costly. So what you can do is if you go through all the Node modules you're requiring in your Electron app, and you find out the ones that are not absolutely necessary for the app to start up properly and to show the first screen, and you wrap those calls in a set timeout to delay them. So then it will show the first screen first, and then it will do all the other requires. That would actually speed up your startup time quite significantly, especially if you have a lot of modules being required. So to answer the original post question, is Electron the perfect solution to a desktop application? Well, we have discussed quite a few caveats of developing with Electron, and it's certainly not perfect. But if you have evaluated your need and that you decide you want to build a desktop app, you want it to be cross-platform, and you want to build it fast, and you don't want to learn, you want to use the web tech knowledge that you already have, then yeah, I think Electron is the best battery-included tool for the job. And once you have decided to use Electron, I hope this talk has equipped you with more knowledge and tools that you can use to navigate this desktop landscape. That's all I have time for. Thank you very much for your attention.